The universe is stranger, more marvelous, and vaster than we can truly comprehend. That quote. Wow, it really captures the feeling, doesn't it?
It certainly does. It's humbling, actually, when you just stop and think about the scale, the
Yeah.
sheer weirdness of it all.
Exactly. And that's what we want to explore today, not just, list definitions of astronomical objects.
Right, more like digging into the stories behind them.
Yeah. How they form, what makes them tick, why they're so fascinating. It's kind of an insider's tour of the cosmos, focusing on the really cool bits.
And we've pulled together quite a bit of material for this, haven't we? From basic wiki entries to cutting-edge NASA stuff.
Oh, yeah. We've got the Wikipedia basics on astronomical objects, those amazing NASA explanations on nebulae, updates from the Perseverance rover on Mars.
University classifications for galaxies, articles thinking about life out there.
And this massive overview doc that touches on, well, pretty much everything from rogue planets to black holes. It's a lot to weave together.
It is. And, it's worth remembering how far we've come in understanding all this.
Oh, absolutely. That history bit in the Wikipedia article, it's wild.
Oh, yeah.
Thinking that ancient cultures saw these as gods. And now we've got telescopes in space, rovers on Mars analyzing rocks. What a shift.
It's a huge leap from pure mythology to actual, scientific evidence and observation.
Okay, so to get us started, let's nail down a basic term. What exactly is an astronomical object?
Good place to start. So Wikipedia makes a useful distinction. We often say object and body interchangeably, right?
Yeah, sounds about right.
But technically, in astronomy, a body is usually a single thing held together by its own gravity, like a planet, a star, an asteroid.
Okay, one distinct thing.
Exactly. Whereas an astronomical object, well, that's broader. It can be a more complex structure, maybe not even fully bound by gravity. Think galaxies, star clusters, nebulae, those are objects.
Ah, I see. So an object can contain multiple bodies, even other objects.
Precisely. Like our solar system is an object containing the sun, planets, which are bodies, and so on.
Okay, got it. So Earth is a body, the solar system is an object. What about something like a comet? That seems in between.
Good question. Yeah, a comet's nucleus. The icy rock bit, that's a body. But when it gets near the sun and grows that big fuzzy coma and tail, the whole thing could be seen as an object. It shows how these definitions can be a bit fuzzy sometimes.
Makes sense. Okay, so how are all these different objects arranged? It's not just random, is it?
No, not at all. There's a definite structure. The Wikipedia section on Galaxy and Larger talks about this hierarchy. Galaxies themselves, these huge star cities, they clump together.
Into groups and clusters?
Exactly. Galaxy groups, then bigger galaxy clusters. And even these clusters aren't spread out evenly. They form even bigger structures called superclusters.
Wow. Like cosmic neighborhoods getting bigger and bigger.
That's a great way to think about it. And these superclusters, they're linked up, forming these long, sort of thread-like structures called filaments.
Filaments.
Okay. And in between these filaments are relatively empty areas called voids. This whole network, filaments and voids, that's what we call the cosmic web. It's the universe's large-scale architecture.
The cosmic web. I like that. Okay, let's zoom in a bit. Let's talk galaxies. We see these incredible pictures, all different shapes. How do we classify them?
Right. Well, the classic system comes from Hubble, based on what they look like. The University of Western Australia source lays this out nicely. You've got elliptical galaxies first.
Ellipticals, smooth, sort of blob-like.
Pretty much. Smooth, oval shapes, mostly older stars, not much gas and dust for making new ones. Then you have lenticular galaxies.
Lenticular, like a lens.
Exactly. They're kind of a mix. They have a central bulge and a disk, like spirals, but no obvious spiral arms.
Okay, and then the famous ones, the spirals.
Yep, the pinwheels. They have that central bulge, a flat rotating disk, and those characteristic spiral arms. That's where lots of new stars are forming, full of bright young stars, gas and dust. Our Milky Way. That's a spiral.
Our home galaxy. And it's huge, right? Something like 100,000 light years across.
Roughly, yeah. And maybe 1 trillion times the mass of the sun. Just staggering numbers.
Mind-boggling. And we're not alone out here.
Nope. We've got neighbors. The large and small Magellanic Clouds, you can see them from the southern hemisphere. They're smaller, irregular galaxies orbiting us.
Satellites, kind of.
Sort of, yeah. And then our nearest big neighbor is Andromeda. Another spiral galaxy, about 2.5 million light years away.
And we're heading towards each other.
We are on a collision course, actually. But don't worry, it's billions of years away. Plenty of time.
Phew. Okay. And all of us, Milky Way, Andromeda, Magellanic Clouds, others were part of the local group.
That's right. Our local cluster of maybe 50 or so galaxies, all bound by gravity. And there are weird galaxies out there, too. That Bunyashot TXT source mentioned the Black Eye galaxy.
Yeah, what's its deal?
It has these gas disks rotating in opposite directions, which is really strange. It strongly suggests it swallowed another galaxy sometime in the past.
Whoa, so you're seeing the leftovers of a cosmic crash.
Pretty much. Okay, how about we move to something maybe even more beautiful, nebulae? NASA's decoding nebulae piece really makes them shine.
Oh, the pictures are always stunning. So what are they fundamentally?
They're essentially just giant clouds of gas and dust floating in space. But, as NASA explains, they're incredibly important. They're both stellar nurseries.
Where stars are born.
And stellar graveyards, in a way, the remnants of stars that have died.
Birth and death, all in these clouds.
Mm.
And they look different. Some glow really brightly, others are dark.
Exactly. Different types, different reasons for how they look. You've got emission nebulae first. They glow because the gas inside is heated up, ionized by hot young stars nearby.
So the stars make the gas light up.
And they light up in specific colors depending on the gas, like in the Eagle Nebula or the Carina Nebula. Oxygen often looks blue, sulfur red, hydrogen, and nitrogen green. So looking at the colors tells us what's in the nebula.
Cosmic chemistry. Okay, so that's emission. What about reflection nebulae?
Right, they don't glow on their own. They're like cosmic fog scattering the light from nearby stars. NASA uses the headlight analogy.
So they just reflect starlight.
Exactly. And they often look bluish, like NGC 1999, because the dust particles scatter blue light more effectively than red light.
Okay.
Yeah.
And then the dark ones.
Dark nebulae, that's just where the dust is so thick, so dense, it completely blocks the visible light from stars behind it. Like Caldwell 99, it's just a silhouette against the starry background.
So empty-looking patches that aren't really empty.
Precisely. Then you have the end-of-life nebulae, planetary nebulae.
Despite the name, nothing to do with planets, right?
Right. Bit of a historical misnomer. They're the outer layers puffed off by dying stars like our sun. The Helix Nebula is a famous example. The dying star's core, a white dwarf, lights up the expanding gas shell.
A star's final, beautiful breath. And supernova remnants. More violent.
Much more violent. That's the debris cloud from a massive star exploding. The Crab Nebula is the classic. It's still expanding. And there's a pulsar, a spinning neutron star at its heart, powering the whole thing.
Wow. And OIST.txt mentioned the red ribbon, too, from an old supernova.
Yeah, supernova 1006. And within many nebulae, like the Eagle Nebula's Pillars of Creation or Rho Ophiuchi, the whole cycle starts again. New stars are forming right now.
It's constant recycling. Amazing.
It is. And NASA points out how crucial different telescopes are. Hubble, Chandra, Spitzer, now Webb. Seeing in different kinds of light, like infrared or X-ray, shows us things hidden in visible light. We get the full picture.
Which brings us neatly to the stars themselves. Born in nebulae, as the school's observatory says. And we classify them using that diagram, Hirschsprung-Russell.
The HR diagram, yeah. It's fundamental. You plot a star's brightness, its luminosity against its temperature or color.
And where a star falls tells you something about it.
A lot. Most stars, like our sun, fall on the main sequence. That's where they spend most of their lives, fusing hydrogen into helium in their cores. Its position tells you its life stage, its mass, its temperature.
So it's like a stellar census.
Yeah.
And a star's life story is basically set by its mass.
Pretty much, yeah. Mass is key. Low-mass stars, like the sun, have one path.
They eventually swell up.
Right. They run out of hydrogen in the core, swell into red giants, then gently shed their outer layers. That's your planetary nebula, leaving the core behind as a white dwarf.
And our sun does that in about 5 billion years.
That's the estimate, yeah. Still got a while.
Good to know. What about the big stars, the heavyweights?
Much shorter, more dramatic lives. They become supergiants. They can fuse heavier elements, carbon, oxygen, all the way up to iron.
But iron is the end of the line.
For fusion energy, yes. Fusing iron consumes energy, so the core collapses. Boom. Supernova.
And what's left after the explosion?
Depends on the mass. Could be an incredibly dense neutron star, or if the star was massive enough, a black hole. Betelgeuse, that bright red star in Orion, it's a red supergiant, could go supernova relatively soon, cosmically speaking.
Whoa. And sometimes the explosions are even bigger, hypernovae.
Yeah, even more energetic, linked to the most massive stars, maybe forming certain black holes or gamma-ray bursts. Just immense power.
The universe really does go big. And Exoplanets.txt lists this whole zoo of weird stars, too.
Oh, absolutely. You've got brown dwarfs, failed stars, not quite massive enough for proper fusion.
Almost stars, but not quite.
Right. The neutron star is unbelievably dense. Imagine the sun's mass crammed into a city-sized ball. Pulsars are spinning neutron stars beaming out radiation.
Like cosmic lighthouses?
Exactly. White dwarfs, the remnants of sun-like stars. And apparently the universe isn't old enough for any white dwarf to have cooled completely into a black dwarf. That's still theoretical.
Even dead stars take time to cool. Any other oddballs?
Well, there are theoretical ones like quasi-stars from the early universe, maybe with black holes inside. Antimatter stars, imagine that meeting regular matter.
Boom.
Big time. Then there's Tabby's star, still unexplained, with its weird dimming. And the hypergiants like Stephenson 218, just monstrously huge and bright, really testing our models of star formation.
Pushing the limits.
Definitely. And of course, binary stars, two stars orbiting each other. Super common, actually.
Wow, what a range. Okay, let's move outwards from the stars. Planetary systems. Ours is just one example.
One of countless examples we now know. They form from those dusty disks around young stars, protoplanetary disks. Stuff clumps together, gravity pulls it in. Eventually you get planets.
And our solar system has the rocky inner planets, the gas and ice giants further out.
Dwarf planets, moons everywhere, asteroids, comets, the Kuiper Belt, the Oort cloud way out there. It's a whole system.
And even here, some things really stand out. Jupiter acting as a shield, apparently.
Yeah, its huge gravity probably deflects a lot of comets and asteroids that might otherwise hit the inner planets, including us. Thanks, Jupiter.
Good old Jupiter.
Yeah.
And Saturn's rings, obviously. And its moons. Titan, Enceladus.
Fascinating worlds. Titan's got a thick atmosphere, lakes of liquid methane, and Enceladus. That recent news about potentially finding phosphorus in its hidden ocean, that's huge.
Phosphorus, a key ingredient for life.
As we know it, yes. Makes Enceladus an even more compelling place to look for life.
Amazing. And then, exoplanets. Planets outside our solar system. Thousands known now. Earth Sky even floated the idea that super-Earths might be better for life than Earth.
Yeah, it's an intriguing idea. Super-Earths are bigger than Earth, smaller than Neptune. The thinking is being bigger might mean they hold on to internal heat longer, driving plate tectonics and regulating climate. Maybe thicker atmospheres, too, for protection.
More stable, potentially?
Possibly, and they seem to be really common out there.
And the variety is just mind-blowing. We in Utah TXT and Earth Sky lists some wild ones. Kepler 452b, Earth 2.0.
Yeah, potentially rocky in the habitable zone of a sun-like star. Then there's Gliese 667cc, TRAPPIST-1 with 7 rocky planets.
7. Some in the habitable zone.
Several, yeah. It's an amazing system. But then you get the really strange ones. WFP12b getting eaten by its star. Draugr orbiting a pulsar? How does that even happen?
Right. In HD 189733b, raining glass. Sideways.
Molten silicate, yeah. And J4407b with rings hundreds of times bigger than Saturn's, Kepler 22b, GJ1214b, maybe an ocean world, even an unconfirmed one, KOI 4878.01, that looks very Earth-like.
The diversity is just incredible. Planets everywhere and all sorts of weird configurations.
Totally. And don't forget rogue planets like OTS-44 just wandering interstellar space alone.
Wow. Which, again, brings up the life question, and we're getting closer to answers, maybe. That Enceladus news, finding more evidence for a wetter early Mars.
Yes, evidence from orbiters, rovers like Zhurong suggesting past lakes, maybe even oceans on Mars.
And Perseverance in Jezero Crater, finding organic molecules.
Yeah, in rocks that formed from magma and interacted with water. Now, organics don't automatically mean life. The scientists are very clear about that.
Right. Building blocks, not the building itself.
Exactly. But it shows the ingredients were there, and conditions might have preserved signs of life if it did exist. Makes getting those samples back to Earth even more exciting.
Definitely. It paints a picture of our early solar system being potentially quite lively in places.
Potentially, yes. Much more dynamic than we might have thought.
Okay, panning back out again. Beyond individual galaxies, you said they cluster together.
Right. Into galaxy groups like our local group, then bigger galaxy clusters. And these clusters group together into superclusters. It's levels upon levels.
And the biggest structures of all are those filaments and voids, the cosmic web.
That's the largest scale structure we observe, yes. Immense filaments of galaxies and clusters, separated by vast, relatively empty voids, like the KBC void mentioned in the notes.
And these massive structures can do strange things, like gravitational lensing, creating Einstein rings.
Yep. The gravity of a huge cluster can bend the light from a galaxy far behind it, distorting it into arcs or even a complete ring. It's like a natural telescope.
Nature's telescope.
Yeah.
Cool. And Higgs and compact groups. Really tight-knit galaxy group.
Incredibly dense, yeah. Galaxies practically bumping into each other. And the Pandora cluster, that's where multiple clusters have crashed together. Studying it tells us about dark matter distribution and lets us see even more distant objects through the lensing effect.
So even these huge structures are still evolving, crashing together.
Absolutely. The universe is definitely not static.
Okay, wow. We have covered so much ground. But there's still a few iconic, really intriguing objects we should probably highlight. Black holes had to be top of the list for many people.
Can't talk cosmic objects without black holes. Regions where gravity just wins completely, nothing escapes, not even light.
We know there are different sizes. Stellar ones from collapsed stars.
Intermediate mass ones, still a bit mysterious. And the supermassive ones at the heart of most galaxies, like Sagittarius A in our Milky Way, or the one in M87 that we actually got a picture of.
That first image? Incredible. They have the event horizon, the point of no return, and the singularity inside.
Exactly. And sometimes when these supermassive black holes are feeding, they create quasars and blazars.
Right. What's the difference there? Both super bright.
Incredibly bright. They're active galactic nuclei, or AGN. Basically, the central region of a galaxy where the black hole is actively swallowing gas and dust. This material heats up immensely as it spirals in, blasting out radiation.
So it's the feeding frenzy that makes them shine.
Pretty much. A blazar is just a quasar where one of its powerful jets happens to be pointing almost directly at us, so it looks extra bright.
Got it. We also shouldn't forget things like Omega Centauri, that huge ancient cluster of stars.
A globular cluster, yeah.
Yeah.
Millions of old stars packed together. And our neighbor, the Large Magellanic Cloud, it's a satellite galaxy, but it has some seriously massive stars, like R136A1.
And speaking of massive, IC 1101, one of the biggest galaxies known.
Just enormous, yeah. And think about Oumuamua, our first confirmed interstellar visitor just passing through.
That was wild. And Comet 67P, visited by Rosetta, finding complex organics.
Yeah, amazing mission. Showed us comets are more complex than we thought, and even closer to home, Ceres in the asteroid belt.
The biggest asteroid, right? But more like a dwarf planet. With ice.
Evidence for water ice, maybe even cryovolcanism, ice volcanoes. And Arakoth, the most distant thing we've actually visited with a spacecraft.
New Horizons flew past it after Pluto.
That's the one. Then there's V838 Monocerotis, that star that had a bizarre outburst, creating a stunning light echo. And the Cygnus Loop, a gorgeous supernova remnant. The list just goes on.
It really does. The universe is just overflowing with cool stuff.
Rimming with surprises, absolutely.
So wrapping up this deep dive, it feels like the main takeaways are just the sheer scale and the incredible variety of everything out there, from little moons to galaxy filaments stretching across the cosmos.
Absolutely. And the fact that it's all dynamic, nothing's really static. Stars are born, they die, galaxies collide, planets form and change. It's constant evolution.
It really is. Which leads to a final thought, I guess. With everything we've talked about, this unbelievable diversity, the hints of habitable places beyond Earth, how do you think our understanding of our own place in all this will change in the next few years, decades?
That's the big question, isn't it?
What discoveries could fundamentally shift how we see ourselves in the universe?
Well, yeah.
Well, it's kind of mind-bending to think about what else might be out there, just waiting.
It is. It really speaks to why we keep exploring, why we keep looking up. The potential for discovery, it feels limitless sometimes.
So if anything we talked about sparked your curiosity, definitely dig deeper. Pick a nebula, an exoplanet, a weird galaxy. There's so much more information out there. The universe is waiting.